Knowing whether you're going to get a precipitate or not is a very useful skill to gain, because it could be in a manufacturing process or in the environment. Will you get a precipitate? And there are a lot of issues that go along with that if you do get a precipitate, both chemical and physical issues. So we can go ahead and we can memorize this whole table of different compounds. So we'll know, oh, we're going to get a precipitate or not. But that's not for me. Instead, I would prefer, and this is what I do, I just know two rules. Two solubility rules get me through 99% of these problems. Okay? Here's the first rule. What cations can never, ever form a precipitate? Just know these cations. Whenever you see them, you know you cannot form a precipitate with them. And if you take a look at the solubility rules, they're right here. They are essentially our alkali metals. Lithium, sodium, potassium, rubidium, right? Right, all these ions, the most common ones. Cesium. But there's another one. Ammonium. So just remember the alkali metals and ammonium, these salts, they will always dissolve 100% in water if they contain any of those cations. Now the anions. There are some anions that will never, ever form a precipitate. They're always 100% soluble in water. And here they are. Nitrate, acetate, chlorate, perchlorate, those four. These anions will never ever form a precipitate. Let's take a look at an animation here and see if we can do some predictions as to whether we're going to get a precipitate or not. Let's see if we can predict a precipitate. So let's try this first two solutions. Let's mix sodium chloride and silver nitrate. So if we mix sodium chloride, an aqueous solution of it, and an aqueous solution of silver nitrate. First, why are these two solutions soluble in the first place? Well, you recognize the sodium, right, soluble with everything. The nitrate, soluble with everything. So that's why these are aqueous solutions. They're 100% soluble. So if we mix these two solutions, what's the only possible precipitate you could get? Well, the sodium can't form a precipitate with anything. The nitrate can't form a precipitate with anything. Your only choice is the silver ion and the chloride anion. Silver chloride. That's your only choice. Let's try it. Silver chloride.
When solutions of 0.1 molar sodium chloride, NaCl, and 0.1 molar silver nitrate, AgNO3, are mixed, silver chloride, AgCl solid, precipitates.
So you can see the silver chloride starting to form there. Let's try another one. Let's try silver nitrate and potassium hydroxide. Silver nitrate, and that's aqueous because of the nitrate, and potassium hydroxide, and that's aqueous because of the potassium. What's the only possible solid that you can form here? Nitrate with nothing, potassium with nothing. The only possibility is the silver hydroxide. Silver nitrate and potassium hydroxide. There it is, silver hydroxide.
When solutions of 0.1 molar silver nitrate, AgNO3, and 0.1 molar potassium hydroxide, KOH, are mixed, silver hydroxide, AgOH,
silver
solid, precipitates.
Precipitating out of solution. Get this nice crystal going on in the background. One solution left. Sodium chloride and potassium hydroxide. Sodium chloride and potassium hydroxide. What precipitate can we form? Well, sodium can't, right, make precipitates. Potassium can't. Well, it looks like there isn't anything, right? Because all you have left are two anions. They're not going to form precipitate. Let's try it. Nope. So when you mix the two, those ions just stay in solution. We don't get a precipitate to form. So essentially, here's our homework question. Answer this question. If we mix these two solutions, and they will give us volumes and they'll give us concentrations, should we expect a precipitate to form? So here's our game plan. First, let's write the KSP reaction for a plausible precipitation reaction. Figure out what you think that solid is going to be, okay? And then write its KSP reaction, okay? And then once you do that, go ahead and calculate the KSP. Now we're calling it QC because we don't know if it's at equilibrium or not. But it'd be the concentration of one ion to its power, concentration of the other ion to its power, divided by 1. Find what those concentrations are, calculate them, right? Raise them to the appropriate power, and we will get a number. And that's why we call this QC, reaction quotient, instead of KSP, because we don't know if we're at equilibrium or not. So that's why we call it QC. So we calculate this QC, we get this number, this pretend KSP number. And what we do is we look up in the table for that solid, we find its solubility product. We find its KSP. And we compare it to the QC we just calculated. So there's only 3 possibilities. If it equals KSP, we're at equilibrium, and yes, we expect to precipitate. There won't be a lot, but we should see some powder in there. The other possibility is our reaction quotient, our QC, is less than KSP. And remember, these are products over reactants. If it's too small, that means we don't have enough product, right? We don't have enough. We need more ions. So there's no way we're going to get a precipitate. More is going to dissolve. We're going to get more ions in the solution. The last possibility, our reaction quotient is bigger than KSP. Now we have too much product, right? We have too much product. This number is too big, so the reaction has to go back this way. We're definitely going to get a precipitate then, if we mix those two solutions. So I think this will make more sense if we go ahead and try some of these. Okay, let's try to predict whether we're going to get a precipitate or not. We'll start out kind of easy. From each of the following ion concentrations in a solution, predict whether a precipitate will form in a solution. So all we have are lead ions and chloride anions. We have lead ions and chloride anions. Well, what's the precipitate you can form? Right, that charge has to go over here, this one down there. PbCl2. Right? So we know the concentrations. Let's calculate a QC and compare it to KSP. So what is my KSP for lead chloride? For lead chloride, it looks like it's 1.6 times 10 to the negative 5. Okay, so if I calculate a QC, QC is products over reactants. Lead chloride squared all over 1. So my lead, they said, was 0.035. My chloride was 0.15, but it has to be squared. So what is my QC? My reaction quotient will be 0.035 times 0.15 squared, about 7.86 times 10 to the negative 4. So that's my QC. Here's my KSP. Which situation do I have? My QC, 10 to the negative 4, it's bigger than KSP. If my QC is too big, I have too much product, all right? It's going to shift to solids. I'm going to get a precipitate. So if I have solutions of lead, 0.035 molar lead, and 0.15 molar chloride, I better expect to have a precipitate in that solution. Okay, here's a more general type of problem you're going to see a lot of in the homework. A 45 ml sample of barium chloride was added to a beaker containing 75 ml of potassium fluoride. Will a precipitate form? Okay, the game plan here, get an idea, get a prediction of what the solid is, so we can write a KSP reaction. What solid could possibly form? Okay, now you know that potassium, according to our rules, can't make a precipitate with anything. So that means fluoride has to be one of them, right? So we need a cation over here. We need to use the barium. So our only choice here is the barium with the fluoride. The barium, and the barium has a +2 charge, right? The 2 goes up top. The barium has a +2, fluoride has a -1, so I have BaF2. Goes to barium ion and 2 fluorides. Okay? So my QC is going to be the concentration of barium times the concentration of fluoride squared over 1. So barium fluoride, I need to see what my KSP is for barium fluoride. My KSP for barium fluoride is what? Barium fluoride, 1 times 10 to the negative 6. Okay. So let's figure out what the concentration is of our barium, figure out what the concentration is for the fluoride, plug them in, and get a QC, compare it to KSP. So the concentration of my barium would be the moles of barium all over the total volume. You see what the trick is to doing this? The moles of barium, it's right here. If they gave us the volume and the concentration, so we'll have 0.045 liters times 0.0015 moles per liter. The total volume is going to be 45 mils and 75 mils, because I dumped those two solutions together. So 0.045 plus 0.075 liters. So my barium concentration is going to be 0.045 times 0.0015 divided by, parentheses, 0.045 plus 0.075. I get about 5.63 times 10 to the negative 4. Now let's do the same thing to get the fluoride concentration. Concentration of my fluoride is going to be the moles of fluoride all over the total volume. The moles of fluoride, so we're going to get it from right here. 0.075 liters times 0.0025 moles per liter divided by the total volume, which is 0.075 plus 0.045 liters. 0.075 times 0.0025 equals that, divided by, parentheses, 0.075 plus 0.045 1.56 times 10 to the negative 3. So now I can get my QC. Barium times fluoride squared. Barium, we said, was 5.63 times 10 to the negative 4. Fluoride has to be squared, 1.56 times 10 to the negative 3. I got to square it. All right, just substituting into my QC expression. So let's square. Get about 1.37 times 10 to the negative 9. That's my QC. 1.37 times 10 to the negative 9. My KSP is 1 times 10 to the negative 6. So QC is less than KSP. I need a lot more ions. I need a lot more product to get a solid. So even more is going to dissolve. So there's going to be no precipitate. Okay, now you try this one. A 65 ml sample of 0.01 molar lead-2 nitrate was added to a beaker containing 40 ml of 0.035 molar potassium chloride. Will a precipitate form? Okay, remember the game plan. Pick your precipitate. Calculate a QC. Compare it to KSP. There's your game plan. Try it. So you know nitrate can't form precipitates. Potassium can't form precipitates. Your only choice is the lead and the chloride. And notice the lead has a +2 charge. Chloride has a -1 charge. So let's get the concentration of that lead and the concentration of the chloride. See if we can get it to work. Because our QC is going to be lead concentration times chloride squared. Okay? Let's get the lead one first. It's going to be volume times concentration, but it has to be in liters. 0.065 times 0.01 divided by the total volume, 0.065 plus 0.04. 0.065 times 0.01 equals, divide by, parentheses, 0.065 plus 0.04, 6.19 times 10 to the negative 3. There's my lead. Let's get the chloride. Chloride, moles over liters, 0.04 times 0.035 divided by the total volume, 0.04 plus 0.065, 0.04 times 0.035 equals, divide by, parentheses, 0.04 plus 0.065, close parentheses, equals 1.33 times 10 to the negative 2. Okay, so now I can get my QC. My QC, lead is right here, 6.19 times 10 to the negative 3. Now I got to square the chloride, so times 1.33 times 10 to the negative 2, but it has to be squared. squared times 6.19 times 10 to the negative 3, about 1.1 times 10 to the negative 6. So let's compare QC to KSP. What is that number? KSP, I'm looking for lead 2 chloride. Here's lead 2 chloride. Oh, I was just looking at that. 1.6 times 10 to the negative 5. 1.6 times 10 to the negative 5. I had 1.1 times 10 to the negative 6. It's a little bit too small, right? QC is less than KSP, just barely. So it's too small. I don't have enough product. I can get more product before I get a precipitate. So no precipitate. We're close, but no precipitate. Here's another one. A 25 ml sample of 0.0012 molar sodium sulfide was added to a beaker containing 48 ml of 0.005 molar iron 2 nitrate. Will a precipitate form? Okay, identify what the possible precipitate is and calculate a QC from the KSP reaction. Sodium can't do jack, either can nitrates. So all that leaves is my iron, and the iron has a +2 charge. The sulfide has a -2 charge. So that's my only possibility here. It's the iron and the sulfide. All right, so my QC is products over reactants. I just got to get that iron concentration and that sulfide anion concentration, and I'll have it. So that sulfide concentration, volume times concentration, I'll have 0.025 liters times 0.0012 moles per liter. The denominator is the total volume, 0.025 plus 0.048 liters. 0.025 times 0.0012 equals, divide by, parentheses, 0.025 plus 0.048, close parentheses, equals about 4.11 times 10 to the negative 4. There's my sulfide. Let's find the iron. Okay, now we're going to use its volume and its concentration. 0.048 liters times 0.005 moles per liter divided by the total volume, and that's just 0.048 plus 0.025 liters. I get about 3.29 times 10 to the negative 3. So my QC now will be iron, which is 3.29 times 10 to the negative 3 times sulfide, and that's 4.11 times 10 to the negative 4. Well, 1.35 times 10 to the negative 6. So let's compare QC and KSP. What is that KSP for iron sulfide? Iron sulfide is about 6 times 10 to the negative 18. Well, our QC is way too big. right? We have way too much product. It's going to shift towards the solid. Definitely, we are going to have a precipitate. So our objective for this set of problems is to pretty much take a look at the solutions you're given and predict what the precipitate's going to be. And calculate the concentrations of those ions that you believe are going to form the precipitate, and calculate a QC, then compare it to our KSP in the table, and see if you get a precipitate or not.